Alright, this is Unit 1 in AP Stat, and we're kind of diving more in with Chapter 5. And the most recent videos we're dealing with standard deviation and the sample versus population, as well as now we are on sample variance and sample population with our items, and this is our basically dealing with our variance as well. And we even hit on things like range as well to see the difference between them. But here is a fact before we continue on. Variance is not listed on the calculator, but all you have to do to get it is basically square your standard deviation. So when you go and you look under your column, you'll see standard deviation there. Just square that number and you will have your variance. Things to remember about standard deviation. Close data will have a small standard deviation since it's closely grouped together. Their variance, their distance apart from each other, is not going to be very big, right? Spread out data will have a larger standard deviation. Think about our bank examples. Bank 1 and 2, really small, if not even existent standard deviation because the numbers were close together. But the spread was much bigger when we were talking about Bank 3 because we had a 1, a 3, and a 14, right? Much bigger, much larger spread. If the standard deviation is small, the data is grouped around the mean. That's what it means. So the smaller your standard deviation, all right, then the data is mainly focused around your mean. If the standard deviation is really large, the data is spread out from the mean, is basically what it means. Do you remember a normal distribution, right? Do you remember that? You might have hit on and experienced something like this in some of your other courses before. And it kind of looked like this when we were talking about it here. The idea of a normal distribution. There is no skew whatsoever. Think about it. The most common, the mode in the middle, but the middle happens to also be your average, which also is the middle of everything. So it's kind of like the perfect uniform item for us. There's really no outliers. There's really no skews. Like, it's good. If the data fits this shape, it's normal distribution. What we will start to talk about is how this is basically something that you hit on in your other classes. It's called the empirical rule. The empirical rule, or the rule of thumb. And this rule tells us the percent of data falling within each standard deviation from the mean in a normal distribution. All right? The empirical rule. 68% of all data in a normal distribution falls within one standard deviation. Okay? 95% of all data in a normal distribution falls within 3 standard deviations. And 99.7% of all data in a normal distribution falls within 3 standard deviations. If you have to, pause the video. All right, write this down, but this is how the empirical rule works. You are figuring out where a majority of your data will fall, thus making things way past here, outliers. If you're hidden up past 3 standard deviations, the likelihood is 0.3% that something's hanging out there, making it a pretty good outlier of something happening. Will it ever be 100%? Practically, in our class with a finite number of people, the answer is yeah. All right, with a finite number. Theoretically, though, no. Theoretically, no. It's never going to be 100%, right? What if we did heights in this room and we had an individual in this room who was 8 feet tall, right? Took all the heights of everybody in this room. One of you is an 8 foot tall human being. Theoretically, we should never have 100% of our data covered due to outliers in a population. Okay? Theoretically. But again, practically, sure, yeah. What this is telling us for a normal distribution data set is that it's not very likely that someone is outside of 3 standard deviations. It's just not likely. All right? It's just not likely that you're 3 groupings, measures away from the mean. All right? The average person in a data set. Out of 1,000 people, only about 5 will not be within 2 standard deviations. Is roughly what we're saying. A grouping of 1,000 people, about 5 will be outside of 2 standard deviations. I mean, that's insane when you think about it. Okay, the likelihood that you'll fall within 2 is 995 people. So basically, we can use standard deviation with normal distribution, all right, that we're going to be talking about in those data sets to see where the data is likely to fall and not fall, is what you do. And the empirical rule helps us out even more with this when we are told that it is a normal distribution. Anything that falls within 2 standard deviations is considered normal. Anything. All right? You find the mean, you find your standard deviation. 2 standard deviations out of the mean on either side, that grouping, is classified as being something that is normal. It should occur. It's usually going to happen. Anything that falls outside 2 standard deviations is considered unusual or rare. All right, so graphically speaking, there is your mean, whether it's a sample or population, right? There's your mean. Here is the graph, right? Again, if you got to write this down, pause the video. All right, write it down and move on. Now, since our population is normally distributed, our mean is the center with the standard deviation close. So, I know that this is in the center. A normal distribution will tell you the mean is right smack dab in the center. And on top of that, there's 1 standard deviation away on both sides. 68% of my data will fall in this area, right? That's why we have this plus or minus idea. There's the mean, plus or minus 1 standard deviation, okay? 2 standard deviations, right? Plus or minus 2 standard deviations, and this is 95% of the data, which means usually everything that you have in your data will fall between here. Usually, is what they're saying. 3 standard deviations. From here over and from here over is rare, but everything in the middle works. But taking that into consideration, this is mean plus 3 or minus 3 standard deviations away. And using the empirical rule, this is what it will look like. 68% or 34 and 34. 95% split up, just like this, in each of those quadrants. And 99.3% of everything is in between there. So, as we're looking at this, or sorry, 99.7. 99.7 is between there. This is where we're seeing where the data is. This is the empirical rule if you want to make sure that you write this down. All right? 68%, 95%, and 99.7% of all data is where it's going to fall. Okay? That's what they're implying with this. So let's take a look at another example and let's use this empirical rule. If you are told the mean is 34 pounds and the standard deviation is 8 pounds, what percent of data falls between 10 and 58 pounds? So here's what you do. These problems are simple. We are going to be eventually venturing out into some ridiculous problems, but for right now, this is Unit 1, right? We're only in Chapter 5. This stuff's pretty basic, pretty simple, easy to use, right? So, point is, this is your empirical rule, how everything lays out nice and neat, right? There's the mean, 34. Standard deviation, they said was 8, 8, 8, right? And 8, 8, 8. They want to know, I believe it asked, between 10 and 58. Well, 10 and 58 happens to be that full 99.7%. 99.7% of all data of those weights will be between 10 and 58, right? And how do I get that? You can just add them all up, or you could remember the empirical rule, which is what you're supposed to do. Or we could just find out how many standard deviations each number is away by taking the number minus that each time. So, say 58 minus 34, which is 24, right? Because we are now looking at the number we were looking for in the mean. We subtract them. That distance is 24. And since I know the standard deviation already was 8, I divide them and I can figure out how many standard deviations it was. So 3 standard deviations away. Fun fact, you don't have to be exactly 1, 2, or 3 standard deviations away. For this unit, sure, for the most part we are. Okay? But eventually as we go, you're going to realize you're never exactly 1, 2, or 3 standard deviations away unless you make the data fit how you want it to fit. But you can be 1.3 standard deviations away, 2.976 standard deviations away. Okay? So you can be 3.2 standard deviations away, 1.8 standard deviations away. Think about it. everyone in the world isn't 50 pounds or 18 pounds, right? All right, it's okay to get decimals for standard deviation because you're going to have people who don't weigh exactly what you want them to. Of course not. Now, that won't help us with the empirical approach that we're doing right now because they won't fall in line with everything. But down the line, you're going to see that you can find it whenever you want. So anyway, to find the number of standard deviations away, this is basically what I just did in the last problem. And you can do that too if you want. But basically, you take the distance of the number you have in the mean and divide by the standard deviation, and it'll tell you how many there are away. This gives us the number of standard deviations away from the mean. So let's say I gave you have a height. That's the mean height, and that's the standard deviation. You have a mean weight, and that's the standard deviation of the weight, right? So that's giving them to you. Which one has numerically a larger standard deviation, right? Which one? Because you're looking at it saying, well, that's a larger standard deviation, but is it truly a larger standard deviation in proximity to one another, right? So, weight. We're saying weight is. Which one has more variation? All right, so, again, which one has a numerically larger, right? Weight is numerically larger, right? Just look at it. Numerically, it's larger. Which one has more variance? Well, that's the issue, right? I'm going to figure this out. So the weight is bigger, but the units don't even match. This information is not comparable currently, but there is a way to compare them. It's called the coefficient of variance. Okay? Coefficient of variance. Coefficient of variance compares the sample standard deviation to the sample mean. This is leading us down a path of something that we will eventually get to called a z-score, being able to compare all types of data, all right, to different avenues, different units of measurement to see how they compare. All right, it multiplies by 100 to get a percent. So you take the standard deviation, okay, whatever that is, divided by whatever that mean is, and then multiply it by 100. So if I look at this, it's 3 over 65 times 100, so it's 4.6 is my coefficient of variance, right? And this might be a formula to write down so that you have it. This is leading into something that's kind of like a z-score. And if you look at the weight and divide it, it's 2.3. So this doesn't tell us how the standard deviation varies, but it helps us to compare the data sets to see which one varies more, right? Height varies more since 4.6% is larger than 2.3. So that's how I can see which one actually varies more. All right. Next up, let's take a look at z-scores, percentiles, quartiles, measures of relative standing. All right. And we will start right there when we come back.